Hi, I'm Yotam. This is joint work with Mooly, Sagiv, Sharon, Shoham, and James Wilcox, and it's about IC3 PDR, one of the latest breakthroughs in invariant inference. Published in 2011, it was recognized quickly afterwards as a very, very big thing. So for example, the HVC award from the subsequent year cites reports of leading performance on hardware verification problems and the fact that IC3 has innovated this mature research area in what by now includes not only the verification of hardware, but also adaptations of the algorithm to software verification. So this is wonderful. The question is, why is it wonderful? Surely science holds the answer. Unfortunately, science doesn't tell us much about IC3 PDR. So this is what we have to say about PDR, that it can be roughly understood as an abstract interpretation procedure in an abstract domain that can be expressed using notions from the monotone theory, work by Bshoutys, originally developed in the context of exact concept learning. We were surprised by this because if you look at PDR, it mostly doesn't look like abstract interpretation, and it's significant because it partially answers a very important question about PDR, which is how it is able to overapproximate rather than stick to the set of states that are exactly reachable, a key concern for every invariant inference algorithm. To understand the question of overapproximation, let's talk about the usual explanation of PDR and its central data structure, the frames. So the frames are a sequence of formulas, or equivalently sets of states, that start from the set of initial states and grow monotonically, while not including any bad state, and they have the property that frame I contains all the states that are reachable in the system in I steps. So the first frame contains all the states reachable in one step, the second frame contains all the states reachable in two steps, and so on. When the frames converge, when two frames are equivalent, the algorithm has found an inductive invariant which separates all the reachable states from the bad states, establishing the safety of the system. So this is the usual explanation of PDR and PDR's frames, but something is missing here, because it's not enough to say that the frames just contain all the states reachable in I steps, they must include also additional states. Otherwise, this is not PDR, this is exact forward reachability, and we know that it might take many, many iterations for exact forward reachability to converge to an invariant. So somehow PDR must overapproximate, and in each frame include many additional states beyond those that are exactly reachable. How this overapproximation is performed and what can be guaranteed about it, we want to understand it theoretically. To do so, we introduce lambda PDR, a theoretical algorithm that's a simplification of standard PDR, and study overapproximation in lambda PDR. The reason is that PDR overapproximates at least as much as lambda PDR, so whatever overapproximation lambda PDR performs, it's also performed in standard PDR. We showed that lambda PDR is equivalent to an abstract interpretation procedure in a new domain where the abstraction function takes a set of states and returns the monotone hull with respect to bk, the set of states that can reach a bad state in k steps, and where the monotone hull is a notion from the monotone theory, which is essentially concerned with representing formulas as conjunctions of monotone formulas. More on this in the paper. We showed that this abstract interpretation procedure can lead to significant overapproximation, at times an exponential gap between the number of frames required for lambda PDR to find an invariant and the number of iterations required for exact forward reachability to do the same. Also, we have a similar gap between lambda PDR and the variant of model-based, interpolation-based invariant inference, demonstrating that this overapproximation is really something special in PDR. We also provide general bounds on the number of frames required for lambda PDR to converge, pertaining to syntactic properties of the transition system it's analyzing, bringing together results from abstract interpretation, the monotone theory, and completeness thresholds for bounded model checking. See you at the talk or at the paper. Thanks.